Section 2 is titled Understanding Alignment and contains 8 lessons. In this video we're going to look at first principles of alignment, including how you level a component, set its rotation, and finally its origin in all 3 axes. Level. The first thing we need to do is level the component. This is not a physical levelling, but a measurement of one face using a 3D feature and adjusting the work plane to this face. Let's consider the simple square block used in video 4. Imagine balancing it using a single point in the centre of the block. The block is very hard to balance, rocking from side to side and from back to front. Obviously, this does not provide a stable, level component. In this video, we'll take a closer look at the alignment discussed in video 6 and see how a feature's direction affects alignment. We'll also discuss what happens when the incorrect work plane is selected when setting the alignment. Finally, we'll look again at how each feature is used to create the alignment and useful ways of checking an alignment is correct once complete. With most software, the line may be measured in any direction, but additional work is required before its use. There are 2 ways of achieving this. The first method is to construct a reverse line from the original. The second, software permitting, allows the use of the original line during the alignment but requires the changing of the property defining the direction. For example, rotate the y-axis to the line in a y- direction. In this video, we'll apply the principles discussed in video 7 to another geometric alignment, a cylinder, circle, circle alignment. We'll also look at 6 other common geometric alignments and describe how each of the axes are set. Finally, we'll look at how a plane, line, point alignment is created when the plane isn't measured on the top face. Predefined routines. The software for most CMMs have a set of predefined alignment routines. These can simplify and speed up the alignment process as they allow for a quick and simple alignment with the axes and datum being set within the routine. These routines can be very useful when just starting to program. However, they do not always create the desired alignment, so understanding different types of alignment is crucial to becoming a good programmer. The following are various types of alignment, including most of the predefined routines. In this video, we'll take a look at how an alignment is modified by a datum shift or a datum rotation. We'll look at the different methods of applying those modifications, including using theoretical and measured data and why they may be required. We'll look at 2 different examples of applying alignment modifications and then summarise the lesson. Finally, we'll look at how angular directions are defined for each work plane. Datum shift to an actual position. The second method of performing a datum shift is to move to an actual position by moving to a measured or constructed feature or features. To move the datum to the front left-hand corner and level with the top face, we first need to measure the features that define it. To define the Z0 position, a point is taken on the top face. Let's call this point, point 1. No orientation information is required to set the Z-axis, as this has been previously set. A plane may also be used to set the Z position, but again, the orientation of the plane would not be used. Hi, welcome to video 10, the 5th video in section 2, which is called RPS alignment. In the video, we'll take a look at the fundamentals of an RPS alignment. We'll describe what it is and how the CMM software calculates an alignment by setting measured features to their theoretical values. We'll also describe techniques you can use to help you visualize the alignment and how to create a robust alignment. Finally, we'll summarize the RPS alignment and discuss different methods of using them in practice. As mentioned earlier, with an RPS alignment you need 3 features that capture the X, Y and Z positions accurately. With these 3 points you can perform a type of 3, 2, 1 alignment. First, let's consider the plane feature. The measurement of each of the 3 holes using the non-aligned circle method captures each hole's center position and the adjacent surface position. Hi, welcome to video 11, the 6th video in section 2, which is called car line alignment. First in this video we'll describe what a car alignment is, then we'll look at where and why it may be used. We'll also look at how a local alignment is created on the component, and then how the alignment is modified to create a car line alignment. Finally, we'll discuss why working with a car line alignment can complicate inspection and programming and why additional care is required. The glossary term for car line alignment is included in video 6. Other than that, there aren't any new terms, so let's get started. From a local alignment to a car line alignment. Let's look at the steering wheel. In the image currently displayed, the centre of the steering wheel is positioned at x equals 1200, y equals 400, and z equals 800, and at an angle of 45 degrees relative to the car's datum. To measure the steering wheel individually in a car line alignment, this position would need to be replicated, assuming this is the datum specified on the drawing. Hi, welcome to video 12, the 7th video in section 2, which is called Best Fit Alignments. First in this video, we'll describe what a best fit alignment is, why and when you would select to use one, and the effects using one may have on the alignment's datum position and results of any measured features. We'll look at a 6-point best fit alignment, describing the principles using a simple prismatic component, and then another look using a more complex component. We'll discuss a multi-point best fit alignment and discuss how deviations are spread among the datum features, and how it differs to a 6-point best fit alignment. Finally, we'll discuss some of the practicalities of working with a best fit alignment and a few methods of simplifying their use. 6-point best fit alignment. The simplest form of best fit alignment with a CAD model uses 6 points. The theory for this type of alignment is very similar to an RPS alignment which was discussed in video 10, but uses points in place of non-aligned circles. As with RPS alignments, the theoretical values for each of the points are required, these values being taken directly from the CAD model. CAD models define the geometry of the component and are generally at the theoretical nominal. However, in some instances, they may be modelled on top or bottom tolerance. Hi, welcome to video 13, the 8th and final video in section 2, which is called Alignment Bad Practices. In this chapter, we'll discuss some common alignment errors and bad practices. These bad alignments may appear to give you a true and robust alignment, but once you start measuring and reporting features, the problem may become apparent. These include the effect non-square faces and form error have on a plane, line, point alignment, why selecting concentric circles doesn't work when setting a rotation, setting the rotation to the same axis as the first axis, and when the alignment is rotated about the incorrect axis. We'll also look at the effects of using a short length to set the rotation, and the measurement errors caused when an alignment hasn't been created and work planes haven't been set. The problems occur when the circles used are designed as concentric. As the theoretical position of the holes are the same, the line produced between the centres should be of 0 length, and, as a result, a rotation about the line would be impossible. However, the actual position of the holes will almost always deviate, even if the deviation is only a few microns. Consequently, it's possible to create a line, and the rotation will be set using this very short line. The direction of the line will also be totally random, causing a similar effect in regards to the rotation.